Yeah, hello everyone. Good morning over there. It's a pity that I could not come in the end. I hope you're having a great meeting, and I want to thank the organizers for still giving me the opportunity to join in online and schedule this talk as friendly as possible for given my time zone. What I want to talk to you today is exactly polluted stars, and I want to discuss them from the point of view of binarity and nucleosynthesis. I want to convince you that they have a lot to teach us about these two aspects. Just to put everyone in the same page, when I mentioned polluted stars in general, but I will use barium stars as the prototypical family of these polluted stars. These polluted binaries are stars in the main sequence or in the giant phase that show an enhancement, an overabundance of S-process elements. We know that they are not evolved enough to have produced the S-process elements themselves, because the S-process takes place at the end of the AGB phase, of the asymptotic giant branch phase. And we also know by now that these stars form in binaries and that they are precisely polluted. They were polluted by a former AGB companion that was the one that made this S-process in their interiors. So this is a well-accepted scenario for the formation of barium and related stars. Basically, in a binary system, we have a star that evolves faster than its companion, reaches the AGB phase, makes the S-process elements in its interior, dredge them up to the surface, and pollutes a companion. We are observing these systems at this later stage, in which the primary star in the binary is the polluted star, as I mentioned before, in the main sequence or in the giant phase, and the former AGB companion, the one that made the fun chemistry that we observed in the systems, is now a white dwarf that is traveling along the cooling track, becoming cooler and cooler, dimmer as well, and more difficult to detect. So why do we care about these systems? Well, as I mentioned at the beginning, they have a lot to teach us about what happened before. The stellar and chemical properties of the current components of the system, so the barium star or the polluted star and the white dwarf companion, can really help us constrain nucleosynthesis models. But additionally, the binary properties of these systems also have a lot to teach us, in this case, about the interaction, about how this AGB star interacted with a companion and polluted it. So what I want to do during my talk is basically discussing what we've learned in the last 5-6 years about these systems, show you the most up-to-date observations that we have for them, and discuss them from the point of view of binary and nucleosynthesis models. So I will discuss the stellar and chemical properties of barium stars and related systems, so polluted stars. I will discuss their orbital properties, and I will show you the white dwarf masses that we determined last year for a sample of these binaries. So let's start with the stellar properties of the primary star, the star that we see, that is the polluted star. We located them on a Hertzsprung-Russell diagram. We did this using high-resolution spectroscopy. We did some attempts of doing this just using photometry, but we learned that it was not good enough. So we used Hermes high-resolution spectra, mark model atmospheres, the most up-to-date distances that Gaia had provided us, and we located these polluted binaries on the HR diagram. We have two subsamples, one of dwarfs and one of giants. And we also use starable evolutionary tracks to determine their masses. And from these, we learned that the two subsamples are not exactly comparable in terms of mass. We think that this is an observational bias against finding barium stars in the main sequence at hotter temperatures. From the chemical point of view, we've learned a lot also in the last decade. From the ratio of heavy S-process elements over light S-process elements, we've learned that low mass AGB stars polluted the systems. But we have also built chemical tools to differentiate these stars from others, which becomes quite important when we want to build our sample and use them as tracers for what happened before, right? We have learned that the ratio of zirconium over niobium can help us differentiate polluted stars from intrinsically enhanced S-type stars. And we've also learned that the ratio of lanthanum over europium can help us differentiate them from stars that have been polluted with our process material. This is particularly important for the most metal-poor polluted systems. From the orbital properties, we also have determined the orbits for a significant amount of barium and related stars in the last few years, mainly thanks to the radial velocity monitoring program performed with the Mercator telescope and the Hermes high-resolution spectrograph, but also combining it with older archival data, because the orbits of these systems are very long. As you can see here, we can reach several decades. And even dedicated monitoring programs sometimes are not enough to fit the orbit. From the model point of view, we cannot reproduce these orbits yet. And this is a very dramatic, simplistic view. We can do better than this right now, but it's better to catch attention to show you the extremes. Basically, if we use the most simple mass transfer binary interaction models, what we get is that we expect when an AGB star interacts with a companion, we expect Roche overflow to shrink and circularize the orbit if we take the most classical and simple mechanisms. And on the other hand, if the mass transfer happens via wind, we expect longer orbits, but eccentric only after 3,000 days. As I said, there are a lot of intermediate mechanisms that can alleviate this tension, but I do not think we are there yet. So each new orbit, each new system that we find and pollutes and populates this graph is teaching us something about interaction. There are also ideas encouraging us to think that interactions later with eccentricity pumping agents like a disk, for example, could also, after the AGB has polluted the companion, the orbits can still change and help us solve this. Now I want to talk a little bit about the masses of the companions of these polluted objects, because this is the most recent work I've been doing. These barium stars or polluted stars are normally single-line spectroscopic binaries, which means that if we use the mass function, we can relate the mass of the star that we see, the polluted star, with the mass of the star that we don't see. We do this via this equation. Basically, this side of the equation, we have it thanks to the orbits that we fit. I just show you the eccentricity period diagram. We have the eccentricity, the periods, and the semi-amplitude of the orbits. And we have the mass of the primary star from the Hertzsprung-Russell diagram. I also showed you that plot before. They are still evolutionary masses, so they come with assumptions, of course, including the distances and the parallaxes that are that assume single stars, and we are dealing with binaries, but we have evolutionary masses. We can discuss later how good or how bad we think these are. However, when we are dealing with single-line spectroscopic binaries, we have an annoying inclination factor here that we can normally not solve for. However, if we include astrometry into the picture, we can get inclination information, and then we can solve for the companion mass. We did this for the sample of barium dwarfs and giants. And combining the radial velocity data that we had with Hipparcos and Gaia astrometry, we could constrain the orbital inclinations and the masses of 60 White-dwarf companions of barium stars. Gaia is a very powerful mission, but when you are dealing with the period that we are dealing here, it's not good enough yet. But luckily, these stars have been quite popular for a long time, so they are bright. The classical barium giants, at least, are quite bright. They were seen by Hipparcos too, and the combination of those two is really a gold mine for long period binaries. Just to show you quickly how we did this, we used a code called Orvara, but there are other open software there that allows you to combine your radial velocity. In this example, I'm showing you random barium star with a very long period for you to see again that Hermes alone, a dedicated monitoring program alone was not enough. But when we combine this data with older data, we can do a lot of things. And what we do is fit in a Keplerian orbit through the radial velocity, but making this Keplerian orbit fit as well the right ascension, the proper motion in the right ascension and the declination directions as seen by Hipparcos and Gaia. Like this, we have velocity information in the line of sight and on the plane of the sky, and we can remove that annoying inclination factor that was bothering us. We do this using MCMC techniques, and for this specific system, we could constrain the mass of the secondary to be around 0.94 solar masses. So we did this for as many barium and related stars as we could. And we determined the masses of 60 wider companions. This is the mass distribution of those 60 stars. And we could already conclude some stuff from here about the bulk of the sample, but also about individual objects. So let's discuss this figure a little bit. We found out that on average, this mass distribution, these white dwarfs are slightly more massive than field white dwarfs, but this had already been hinted before, even making strong assumptions to estimate the masses of these white dwarf companions. We expected them to be slightly more massive than field white dwarfs. However, we find significant portion of the sample that are slightly more massive than what we expected. And why is this? Well, I mentioned before that the chemistry is telling us that low mass AGB stars are polluting barium stars, are forming barium stars. However, these white dwarf masses, if we use the latest initial final mass relations for white dwarfs in AGB stars from Paola Marigo, we see that this part of the sample here corresponds to white dwarfs over the 3 solar mass that the nucleosynthesis is indicating that play a role in these systems. This is not very problematic because metallicity is very important, and in this at this moment I'm not taking it into account to tell you this. So analyzing each system one by one, we can see if this works. But the key is that now we have a very strong constraint here with the mass of the white dwarf and the chemical pattern on top of the polluted star, and we can learn a lot about the AGB nucleosynthesis. Worth of cautions are always good. We still have strong correlations between the mass of the barium stars that, as I said before, are evolutionary masses assuming single stars, and the mass of the white dwarf, as well as the separation of the orbit. So we need to use some priors and be careful with these numbers, but we've removed a lot of assumptions comparing with what had been done before. Another fun part of this work is that we found some outliers. So this mass distribution is already the clean one. There is still some interesting guys up here, but we could identify outliers that actually should not be there. This work helped us identify some imposters in the classical barium giant picture. We discarded a star that we determined the secondary mass that was very low, for example. We rechecked the chemistry and we saw that the enhancement was very mild and that it had never should have been never flagged as a barium star to start with. We also identified a triple system. We noticed that one of the shortest period barium giants in our eccentricity period diagram actually had a longer orbit going on here, and we could detect this thanks to the Hipparcos Gaia catalog of accelerations. We noted that there was something going on there on top of the 100-day period that we initially had measured with radial velocities. This system moved from being one of the shortest orbits to being one of the longest, because we also could determine the masses or estimate the masses of the 2 components, and we think that the white dwarf is actually in the outer orbit with a period of about 40 days. So it moved really from corner to corner in the eccentricity period diagram, and this opens also the possibility of learning about how these AGB stars interact with their companions in triple systems as well. And the last outlier that I want to mention is 56 Ursa Majoris. We published a short ANA letter claiming that this star also should have never been flagged as a barium star and could contain a neutron star in the system. So this giant is not accompanied by a white dwarf, or it may not be accompanied by a white dwarf, but it could have a neutron star companion. So if you want more details about the system, I recommend you to read the paper, because we cannot explain all the data that we have for it, but it's actually a very interesting binary. So just to summarize and conclude, I wanted to highlight during these 15 minutes that the orbital properties of barium and other polluted stars can help us constrain evolutionary models, and that each step that we take observationally teaches us something about how these red big stars interact with their companions. Also that the stellar and the chemical properties of these stars can teach us about the process of nucleosynthesis, and there's been quite some work done in Budapest, for example, trying to use these constraints to learn about nucleosynthesis. And of course, worth of cautions, correlations, assumptions. We've removed a lot, but we are still trying to do better. So just keep it in mind if you use our numbers. And that's all I wanted to show you. Thank you for your attention.
Hi, thank you for the talk. This was quite enlightening. So I'm really interested in how you get this orbital distributions of eccentricities and periods, because there just isn't a binary channel that is understood to make things that have, say, 300-day periods. Theoretically, all of these things should be going into common envelope because of the instability of the mass transfer in giants. So the question is, in this type of diagram that you can make for barium stars, you can make it for the Hans van Winkel objects, you know, the post-AGBs plus main sequence star. Mm-hmm. Are there any statistical differences? So we know this pattern very well, but if you look at the details, can you tell that, say, the post-AGB binaries and this sample are different? Or can you differentiate in your sample things that have more massive white dwarf or less massive white dwarf? So are there subsamples that can be seen to be different?
So so comparing the barium stars with themselves, we tried to make correlations, or to find correlations with the amount of pollution, with the enhancement. And yeah, the shortest ones are strongly enhanced and the longest one are more mildly enhanced, but the bulk in the middle, like, it only explains the very extreme, so it was not very useful. Comparing with the post-AGB binaries, they are different. The post-AGB binaries are, for the same periods, more eccentric than the barium stars, but I think this could come simply from the second stage of evolution, right? The barium giants, the bulk, if you remember the HR diagram, they are mostly in the clump, so they've gone up the RGB again, so that gives you a second stage of tidal interaction with the white dwarf, perhaps, that could circularize a little bit more. So that's why I encourage people to look at the barium dwarfs, for example, instead of the barium giants, because we avoid that additional interaction that could make things more complicated. But the post-AGB binaries and the barium stars, the orbits are statistically equally problematic, but statistically different, yes. But I'm not sure what this teaches us, apart from the fact that barium giants could have interacted again. I don't really answer your question, but...
No, that's great. Thanks.
So you mentioned that the primary stars' masses are based on comparisons to stellar models. Have you considered looking at astroseismology of these, like TESS or K2, because they can give...
Yeah, we considered... So when we did this, none of these stars were on the Kepler fields. None of them... So when we did this, we couldn't do that. More recently, I've started looking into that. Now I have found a couple of polluted targets that are K2 giants. So we did some comparisons there with the masses that we infer from astroseismology and the evolutionary masses that we found here. And honestly, for the giants that the tracks are so close to each other there, it doesn't really matter if you're, I mean, of course, the log G from astroseismology is going to be more accurate than the log G from spectroscopy, but the tracks are so close together there that if you are comparing with models, yeah, you don't really do much better. For the two targets that we've done it, the masses agree. Maybe we were lucky, maybe not, but yeah, I have looked into this, but unfortunately not a lot of targets yet can be done with astroseismology.